Okay, thank you very much for having me, and thanks to everyone who's still here. I'll wait for a second for everyone to sit down. Okay, so that's all right. So if I do that, that works, right? Yes. So this is work on curvature regularization with discrete estimators that are called multigrid convergent. That's work that is in common with a doctoral student, Daniel Antunes, who is Antunes, actually, he's from Brazil, but he's a doctorate at Lama, University of Savoie, with Jacques-Olivier Lachaud and myself. So Jacques-Olivier Lachaud is the real specialist on discrete estimators, and I'm here for the optimization. What's the goal of today's talk? Well, we want to minimize a functional, which is relatively well known. It was proposed a long time ago by Euler, in fact, a type of curve that regularized some curvatures. And Mumford, in the 80s, proposed to use them for computer vision. Turns out that these curves that Euler studied are really nice perceptive curves for completing contours. So if you have missing contours in the image, those curves can be shown to have good properties related to perception. And so what they do, those curves minimize a length energy, which depends on the length itself and on the curvature. Kappa is the curvature here, the square curvature. And alpha and beta are parameters. So this is regularized on the boundary, and we have a data fidelity term here. Okay. It's been used a great deal in computer vision for various tasks, for instance, in painting, segmentation, and stereo matching. So these are a few of the people who've studied this functional or variation of it. In particular, in our community, Masnou did that, and many others. So what's the motivation? What do we want to study? I should say a few things, but they will come on. So what do we want to study curvature? What are these properties that I'm talking about that are good at completing contours that are missing? Well, here's an image of a neuron in confocal microscopy. It's very noisy, and we have a large body here, but thin extensions that are axons here. And if I use a really simple-minded segmentation, which is just a thresholding, pure data term, in other words, I get something like that. I get some of the data, but not all of it. So it's reasonable to assume that this is an axon here, even though I have lots of missing data. Now the regularization we all use and love in image processing is the TV, or a variation of it, and that's the parameter term, that's TV, and if we use that term, of course, thin, elongated objects are penalized a great deal because they have lots of contours, and so the result is certainly regularized, but it's not what we want. On the contrary, if we use the elastic completion, the parameter plus the curvature term, the elastica, then we have a good chance of finding a good completion, a good curve. It's not perfect, but it's better. Okay, it's useful. So it's been used a great deal in other contexts. For instance, here, that's an example by Masnou, where that's a natural image. That's a subsampling of the image along a grid. So all the data we have, the only data we have is on this grid. And if we restore the image based solely on that data, basically this is throwing away 80% of the data. We restore an image which looks good. It's not perfect. There are some artifacts in the background. Of course, we've lost the text because there's really no text here, but the reconstruction is okay. In particular, you can see the lines are well preserved, vertical, diagonal, and all that. So it's a really nice result. It's been used in other contexts as well. So we think it's useful. So, okay, but it's challenging, of course. If it were easy, everyone would be using it. Of course, it's easy to optimize if beta is 0, but if beta is non-zero, then that term here is non-convex. Of course, as soon as we have that, here's the problems we have with non-convexity. In addition, we need to find the contours. So it's a kind of a chicken and egg situation. We want to regularize something on the border, and the border is of course not known. So how do we deal with that? So the whole thing is difficult to optimize, and discretization of that term is complex. So it's been studied nonetheless. There are ways to do it, which I will not present here. I could, but if people are interested at the end, have questions, I have a series of papers in the background which I can show. But one thing I want to emphasize is that measuring things in the discrete world is difficult. Here's a well-known counterexample involving discrete measurement. It's called the Schwarz lantern. It's basically the situation here is only to measure the perimeter of a cylinder like this. And if we do our job relatively well, we can get a good estimate. But if we do it poorly, so here's, sorry, it's an animation which I have to stop, and I don't know how to do that. Okay, let me go back to that. Sorry. No. Ah well, I'll leave it running. Okay, so it's going to be slightly annoying, but you get the idea. Okay, so if we discretize this really simple object in the right way, we get 2 pi as the surface, which is what we want. But if we do it poorly, they estimate balloons. It's a very well-known example that was described in the 19th century, so it's not novel at all. And it's a counterexample to the well-known property of Archimedes in 2D, which says that we can, if we take a polyhedron and augment the number of vertices inside a circle, then we get a very good estimate of its length, or its perimeter, eventually. But in 3D, it's not true for a surface. So when we deal with discrete quantities, there's not many properties that we can call upon that are well understood. And one of them is called this multigrid convergence. So what is multigrid convergence? You have 1 second to understand this definition here. Basically, it's a formal definition of the quantity that we want to measure converges to the real quantity we want, underlying quantity, as the step size, or the discretization step, goes to 0. Okay? And if we do that, if we have this property, we can also not only define that this measurement converges to something reasonable, we also usually have an estimate of the speed of convergence. So if we reduce the step by a factor of 2, by how much do we converge to the real measurement? Okay, and so related to that, we want to estimate discrete elements. So for instance here, the one thing we would like to measure, and we will need to do anyway, is an estimator of perimeter. So are there good estimators of perimeters? The answer is yes. There are very good estimators of perimeters. You know the TV estimator for sure. And there are purely discrete discretization of natural. If we say here we have a continuous curve here, and its discretization here in dashed, and inside is the region composed of pixels. And the question here, we can have a convergent estimator of its length, of its perimeter. Can we have the same thing for the curvature? And the answer is yes, we can. And the estimator that's been proposed, there are several, in fact. One of them is a reasonable one called Maximal digital circular arc. It consists of essentially fitting discrete circular arcs to the boundary. And this sounds like a reasonable idea because the radius of the digital circle will provide the inverse of the curvature, obviously. And the difficulty with this estimator is to prove that it is multigrid convergent. And actually that has been done, and it's a good estimator from that point of view. Okay, so now we are armed with an estimator of the perimeter and an estimator of the curvature. Can we use them in a context where we want to optimize a criterion based on them? Okay, so sorry, I forgot that. That's the illustration that the illustration of the proof of convergence consists generally in saying that we can bound the estimate of the curvature, which is given here by two. So you have here a first circle, a first continuous circle, and another continuous circle here, and the proof consists of showing that no matter what the discretization is, you can always provide a cover, which is not in this case rectangular, but it's a series of arcs. It's an arc of circle. It's a crown. And that in this case, the radius is the true radius of the curvature in this portion here is in between those two radii here. And if we can prove that, then it's and with a limited with constraints on the width of this portion of numerical circle, then you can show that as h goes to 0, then this estimation converges to the right radius estimation, and therefore to the right curvature. So it's not very complicated, but it does converge slowly. It converges as the square root of h. But it does converge. Okay, so can we use this estimator for optimizing curvature? All we need to do is to take a discrete version of our criterion, which is here, and take the discrete estimator of the curvature here that we've used. Okay, and so we have also extra constraints. So for instance here, the x's that we consider are binary, inside or outside, foreground or background, basically. And if we use this framework here, it's complicated because it's, of course, an integer quadratic program. And so it sounds difficult to optimize, but in fact, we have been able to, I won't show you the details because that's not what we recommend. That was our first port of call. We had essentially at this point a multigrid convergent estimator of the perimeter and of the curvature. Can we use it to optimize a shape, for instance? The answer is yes, we can do something. We can formulate this as actually as an integer program. We can actually run it, and the question is, does it work? And the answer is, as you'll show, seemingly okay in the beginning. So that's a square in the beginning. So we simulate a curvature flow. It looks kind of okay, and then at some point it's no longer okay at all. So this estimator has good properties in terms of convergence, but it's actually not very good because there's a scale issue when we do the analysis. We would expect that as the radius of the object becomes greater, it would be as if we had a circle with a higher, a lower curvature, and it would behave properly. But in fact, in reality, that's not what we observe. We observe that, in fact, in our analysis, this estimator is too local. And in addition, it was very slow to run. So we had to use another idea. And so the other idea that we've used is simpler, in fact. It's a simpler estimator. It's a really simple idea. If you have a normal curve like this, a curve in a continuous curve, one possible measure of curvature is to fit a real disk near the boundary and consider this area versus the entire area of the circle, of the half circle if you prefer. And it's clearly, if we have a low curvature, this will be close to 1/2, and if we have a lot of curvature, then this will be lower. And that's a really simple way of estimating curvature. And we can show it explicitly by taking a disk. We consider this is the intersection, the area of the intersection between a ball with a shape on the perimeter. P is a point on the perimeter. And if we expand the notation, this expression as a Taylor expansion, the curvature comes up explicitly as a cubic term. And so we can basically provide, kappa is here, provide an estimator by just reordering this formula. Here you have half the area of the disk that I've just described. So it's really quite simple. And the question is now, is this estimator correct? And we have shown that this estimator is actually convergent. It's a good one from that point of view. And now can we use this invariant instead of the one we had before? Okay, so now I will describe the discrete implementation because actually it's more useful. The computations are sometimes a bit onerous, so we only compute, and that makes sense to do that near the border, of course. That's the disk here. Here is the discrete rendering of it. In our current implementation, we are using actual pixels, which turns out to be not such a great idea. Actually, we were working on it this week, but we haven't finished. It's not such a great idea because due to discretization effect, the half circle is not exactly 1/2, of course. And we actually use a disk which is very small, so we have to correct for that, but that's doable. And if we do that, we take care in running the optimization. What we need to do is we have here our original boundary in green, and we consider a larger region, which is basically the dilation of this region. And here, what we want to optimize is really, in some sense, optimize the region, a version of a binary set, Y, which is a binary version of which can be any combination of white and black pixel if you want, 0 and 1 values, such that the curvature at this new boundary is minimized. So that's easy to express in some sense. We basically consider all the possible shape. We consider all the possible, on the boundary of all these new possible shape, we compute the discrete version of the curvature. And among all of them, we choose the one that minimizes the curvature that we have. It's easy to say, but it sounds completely crazy because, of course, that's a problem with a high complexity. So I'm not sure I'm going to describe that all that well in the next slide, but I'll try. Okay. So if we do our job reasonably, we can re-express the squared curvature as with these constants here, and by reordering and removing all the constants, putting together all the things that change, we come up with a slightly better, measurably better version of what we want to optimize. So this is a constant here. That's known. And here, sorry, that's the intersection with the foreground. That's a variable in the regions that we consider. And in this expression here, we have quadratic elements only. Of course, so this problem is a nonlinear sum of binary terms. And it turns out that this expression here under this shape here can be formulated as an LP, not an IP. Of course, it's not obvious that this is an IP, but every product of binary variables can be separated into 3 constraints. And those 3 constraints and a sum. And this renders the problem linear, solvable with using an LP solver. And at least, sorry, an IP solver. But it turns out that this kind of sum here, in this form here, is optimizable with a specific algorithm called a QPBO, which stands for quadratic pseudo-binary optimizer. And that's one extension of GraphCut. QPBO is a GraphCut solver that can deal with some weights that are non-submodular. This is a non-submodular weight that we have here, the equivalent of non-convexity, if you want. And clearly, this is a difficult problem, but this solver can somewhat handle it. QPBO does give you the correct answer if it can compute it. But if it can't, it gives you it doesn't give you an answer. It gives you so when you run QPBO, you may run the risk of having undefined pixels at the end. And so when we run it, we need to be a bit more cautious. In the end, we have a series of solutions that are labeled 1 or 0. And due to this effect, we need to invert the solution, and that's actually our answer. Okay, so that's due to the way that QPBO is implemented. Okay, so now, armed with this new formulation and this algorithm, does it actually work? Okay, so suspense. And yes, it works. So this version of optimization actually does compute a reasonable version of curvature flow. And so, okay, so there are a number of things that we need to say about this, but I'll give you another example. That would be easy to say that with only computing and opening here, but really that's not what it does. Here is an example which is maybe more convincing of a curvature flow which is less trivial. Okay, and that's also useful. Okay, and so now the upshot is, can we do segmentation with it? Yes. So we can use this algorithm with a marker here, and then if we run the pure parameter term, we have this segmentation here, which is not necessarily very nice. And if we add the curvature term, then we have another constraint, which basically takes over the criterion here and ensures that the result is smooth, which is what we want, I guess, in this instance. Here's another example. Okay, so this is the marker, that's the butterfly, and that's the completed segmentation here. All right, so with all this, what's the point? What's the point of all this? Of course, I mean, if you want to use today, I have to be honest, if you want to use a problem that involves Elastica, that's not necessarily the best method that I would recommend. Nonetheless, we have proposed a digital multigrid convergent estimator of curvature. Not only is it multigrid convergent, so it has reasonable properties, but we can also use it as an estimator in a prior, in a discrete variational framework. And we can use this term for segmentation. Of course, it's not finished. Segmentation imposes a result which is binary. And so we need to do some work if we want to use it for regularization, for instance. It has been done in the past. You can, if you have at your disposal only a segmentation method, like a GraphCut, it's possible to show that you can use these segmentation tools as in a framework for regularization. And so we plan to do that. At the moment, our solver QPBO is not really satisfying, because in some instance, if we for some version of alpha and beta, some pixels are not assigned. And so it relies on the idea that the curvature regularization must not be too strong. But this is also the case in most of the literature on this particular issue. So it works very well when on pure curvature flow. It works very well when we have a term composed of perimeter and curvature, when the two are relatively well balanced. But there are cases where we don't have a good convergence not of the estimator, but of the regularization. Okay, so in future work, we have work to do. So the difficulty with it's easy to formulate the problem that I showed before. This one here as an LP. This one here, and it's difficult to solve because this problem as an LP has actually more constraint, as 2/3 more constraint than there are variables. But basically, this problem is essentially balanced in terms of variables and constraints. So it has a lot of constraints. And typically, when you solve an LP, the LP solvers assume that you have either lots of variables or lots of constraints, but not both. And so they use tricks like using a primordial matrix transposition to put themselves in the situation where they have a lower dimensional problem to solve, and then use methods like column generations to find the right constraints. In this case, we can't do that. We have to deal with the fact we have both. But the thing is, the structure of this problem is diagonal, near diagonal. And so we think that we can, there are methods that exist to solve these particular problems, and we haven't tested them yet. So that's our work now. Okay, so, sorry. Also, one of the problems we have dealt with that ends up ensuring that we have some unpleasant or inelegant things to do at the end of the segmentation to end up with a new contour. We want to get rid of that and use discrete calculus to specify a border in between pixels. And in that case, if we do that, when we do that, we'll have a more balanced formulation of the problem. And we want to use this work for restoration. And if we do that, maybe we can dominate the world of digital restoration, perhaps. Okay, so if you're interested in this work, I have a short bibliography, which will be online. It's not very difficult, but I think these are the mostly interesting work in this area in the last 20 years. And I think it's an interesting problem, and it's interesting that even though curvature is a second-order term, which is difficult to estimate, it's interesting to show that you can do it in a purely discrete way. So thank you for your attention.
Okay, so we have time for questions to Hughes.
Do you think we can prove anything about continuum limits of this kind of estimators?
Yeah, it's not obvious. Yeah, at the moment I don't know, but I'd like to. Yeah, continuous limits of this. Normally, the flow that we have should be equivalent to the continuous limit, but it's not easy to show. I agree that. You can show it experimentally, I guess, but that's unsatisfying because the continuous flow that exists, they also use a non-convex optimization method, and so the result is also suboptimal. So if you compare like two suboptimal ways of computing the same thing, it's unlikely you'll get the same results. So now, is the global optimal of this term the same? We interpret the multigrid convergence correctly, at some point, given a fine enough discretization, the answer is yes. That's the whole point. That's the whole point of using multigrid convergent estimators.
So regarding speed of convergence, is anything known in the converse direction? Like it's not possible to go faster than this rate, or?
Yeah, I mean, here we are limited to looking at essentially one step at a time, a small variation around the contours. This assumes that it's a good question because I think Masnou showed not long ago that you can actually consider curvature locally at a particular scale, in meaning that if you want to optimize the curvature of a whole contour, you can consider the current version of curvature to speed up your convergence, depending on what it is. But if you have lots of noise on the contour, then you have to go slow, essentially, which is, I guess, intuitive.
Okay. And what about extension to higher dimension?
Yeah,
like
so
curvature tensors and things like
yes,
this?
Yes, in 3D first, and then 3D would be possible. But we don't have we have, at the moment, in the digital world, we have multigrid convergent estimates of surfaces, of areas. And I don't think we have multigrid convergent estimates of curvature. I mean, because we would have to consider not spheres, but ellipsoids. Because you have to consider there are two curvatures in 3D, and so in theory, if you could fit the best ellipsoid in place, you could use that estimator.
Okay, and it will have the same theoretical guarantee.
Yeah.
Okay. There's no questions. We can. Yeah. No.
It's a bit technical, but when you minimize your formula with the yi, yk, I wasn't sure, because your estimator with the ball is quite nice. It works if you're on the boundary.
Yes, you impose it to be on the boundary.
So here, here you have this formula, but it's P is supposed to be somewhere on the boundary, or
yes,
here?
yes. I'm sorry if that wasn't
so
clear.
So it's A is the boundary, okay?
Yeah.
No.
Oh, sorry.
Okay.
Yeah. So that's the optimization region in O.
Yeah,
the F is the white one. Sorry, you have an.
So what is A? The green?
That's the computation region. That's where you compute now.
Yeah. So it's
okay.
Yeah. So it means your optimization depends on Y, but A depends on Y as well.
Yes.
Okay.
Yes. That's correct.
Okay, so I think it's time to thank Hugh for his talk.
Thank you.